Hey guys, welcome to the review for Business Statistics Exam 1. Do want to apologize about the quality of the scans here. Apparently I don't know how to use the scanner, so I just took a picture of it. So hopefully that'll suffice for you guys. It'll certainly have the content that you're looking for, just isn't in the presentable fashion like I like to normally have it. But this is what we're working with right now, so that's just going to have to be okay. So, basically what I'm going to do is I'm going to get started on this study guide, the study sheet or whatever, and I'm just going to talk through the problems, as many of them as I can, such that we're not kind of going on and on and on. What I'm not going to do is I'm not going to go over these terms on the front page. Okay, this is for you to do. This is for your studying. It's for you to understand the concepts of this, and it doesn't do you guys any good for me to just go read a bunch of definitions. It'll save you legwork, but I actually think you doing the legwork is a good thing for you actually understanding the concepts. If you're just gonna like write down what I'm saying, like there's no thought process. Like, you should go find it, you should read through it. You should make sure that you understand the concepts. So this front page, like in terms of like writing down the definitions or anything like that of understanding, I'm not going to be touching, but I'll let you guys do. And then I am going to be just kind of walking through the questions step by step. Okay, so I'll try to talk through the questions, but you'll have the answers right in front of you. I'll just try to explain the why of why a certain problem is the way that it is. So it's not going to be me solving the problems, because that's already done for you, and you presumably are looking at the answer sheet alongside of this video, or at least looking at your blank sheet alongside the video, and then you can pause whenever you need to. Another thing I need to add is you might hear some noise in the background. Kind of sounds like a construction zone. What I have going on at the house is we've got some people doing some work in the basement, doing some waterproofing, so you might hear a jackhammer, you might hear a truck backing up. They're currently removing loads and loads of kind of rock and concrete from our basement, so I apologize for that. But I wanted to get this to you guys today because there's only 2 more days before the test window, and I just wanted you guys to have the answers with me explaining them. Okay, and so without any further ado, let's get started. I do also want to say, if I go through one of these things more quickly than you'd like, and you still have a question about it, shoot me an email. I'll be happy to answer it. Though I won't be answering any questions on on the concepts once the testing window has started. Okay, so I believe the testing window starts Friday. So once Friday hits, I'm not going to be answering any more questions until the testing window is completed. Okay, sounds good. So let's start walking through the problems here. So for number 1. Which of the following distributions would be likely to model the number of trucks arriving at a warehouse in a particular time interval? Okay, so it's not a normal distribution because it's not a normal distribution because we don't have a mean. We don't have a traditional mean and some standard deviations, and it's not assumed to kind of be a bell curve or anything like that. It's not binomial because we don't have a specific number of trials. Okay, so with binomial, we'll have a specific number of trials, a specific consistent independent probability. Yeah, and it's not exponential because we didn't even learn exponential. Right, exponential is actually related to the Poisson, but we're not going to get into that. Okay, so you didn't even learn the exponential distribution. So if you see that, you're not going to be working on that. Okay, so as you know, it's going to be Poisson because Poisson, if you remember in your notes or in the PowerPoint slides, talks about it is the number of occurrences over a given interval of time, space, area, anything like that. Okay, so Poisson distributed. A variance can never be A, 0, B, larger than the standard deviation, C, negative, or D, smaller than the standard deviation. So it is C, negative. Variance can never be negative. One of the reasons we know this is because if you look at the variance formula, it is, the summation of a bunch of, so first of all, it's a summation, and it's the summation of x values minus mu values squared. Okay, so because we're adding up squared values, we know that we're adding up positive numbers. So then, anytime we're adding up positive numbers and dividing it by some other positive number, we know that we're going to have a positive number. So therefore, it's got to be C. It can't be negative. Another way to give you examples to know that it's not A, B, or D, for 0, the variance could be 0 because all the data could just be 5s. They could just be all the same number, and in that case, the variance would be 0. If you ran through the formula, the variance would be 0. The variance will be larger than the standard deviation if the variance is greater than 1, because then when you took the square root of it, the standard deviation is going to be smaller. So say the variance ends up being 2, and then the standard deviation would be the square root of the variance, and then it's going to be the square root of 2, which is like 1.43 or something like that. And then conversely, for D, smaller than the standard deviation, if the variance was less than 1, say 0.5, and you took the square root of that, the square root of that is going to be higher than 0.5. I don't know it off the top of my head, but it is going to be higher than 0.5. Okay, so number 3, the expected value of a random variable must be an observable value. This is obviously false. An easy example of this would be rolling dice. So if we were to roll one die, we have 6 possible outcomes. We have 1, 2, 3, 4, 5, or 6. Okay, we have 1/6 probability for each one of those occurrences. So what we would do is we would go through that, and we would list the x values, and then we would list the probability of those x values. And then we know that the expected value, or the mu of that, is just going to be the summation of x times p of x. So the summation of the x values times their associated probabilities. Okay, and if we did that, and I think we've done this example before in a prior video, or you've probably seen it on the slides or within Connect. But basically, all that to say, the expected value of that specific event is going to be 3.5, right? So that's the average of rolls. It would be 3.5. Okay, and then the idea is that, well, you could never roll a 3.5. You can roll 1, 2, 3, 4, 5, 6. So 3.5, the expected value of the random variable, is not an observable value. It's not in the sample space. Okay. Number 4, within a given population, 22% of people are smokers, 57% of people are males, and 12% are male smokers. If a person is chosen at random from the population, what is the probability that the selected person is not a male and not a smoker? All right, so the best way to go about a problem like this is you first have to write down what you know and what you are asked to find out, right? Before you make a contingency table, before you do any of that, write down what you know. So that's what you see me do in this problem. Given a population, 22% of people are smokers. Okay, so I just write down probability of S, meaning the probability of a smoker, is 0.22. 57% of people are males. Probability of M is equal to 0.57. Okay, and then this is the crux of the problem, right? Like, so this is the verbiage that you need to kind of make it through, get through the weeds on to figure out. You need to figure out what exactly is the way that we write the probability for this next one. And it says, and 12% are male smokers. All right, so a male smoker would be defined as somebody who is both male and is a smoker. Not given that they're a male, they're a smoker. Not given that they're a smoker, they're a man. A male smoker is somebody who is both male and a smoker. And then that's what you see me put there. So probability of M and S. Okay. So we know, so then So that's that. So if a person is chosen at random from the population, what is the probability that the selected person is not a male and not a smoker? So I didn't write it down, so apologize for that, but that would be the probability of not M and not S. So basically it would look like our probability of M and S, but with just bars over the M and S. Okay. And then the way that I always go about solving these is I use the few pieces of information that we get in the problem. I plot those into the contingency table. Okay. And then I find everything else given the stuff that we have in the contingency table. And this one is actually pretty easy because everything that you see on the screen that is not highlighted is stuff that was given to us in the problem. And then I just used probability rules to figure out the rest. So we see that the 12% of male and smoker is given. The probability of male is given, and the probability of smoker is given. Okay, well, I can just use like the complement rule to find out like the other associated probabilities. Okay, and that's what I do. So I fill in everything, and then lo and behold, the answer is just in the table. Probability of not M and not S, or probability of F and not S, is equal to 0.33. So that's that. Number 5, if events A and B are mutually exclusive, probability of A given B is equal to 0. And the idea is just to know the definition of mutually exclusive. Mutually exclusive is not independent. Okay, independent means that they don't have any effect on each other. So they could both occur at the same time, and they're both not going to have an effect on each other occurring, right? So that's where we get into our multiplication rule of probabilities. So when something is mutually exclusive, just means that they can't occur at the same time. So then the probability of A happening given that B happens, we know is 0 because A can't occur when B happens. Okay. 6. Determine whether the following two events are mutually exclusive: consumer with an unlisted phone number and a consumer who does not drive. So the question is can those happen at the same time? Can you have an unlisted phone number and be somebody who does not drive? Well, sure, right? So then we wouldn't say that they're mutually exclusive. Mutually exclusive would be somebody who, on a given day, and I mean on a specific day, walks to work and drives to work. Well, you can't walk to work if you're driving to work as well, theoretically, if you're taking one mode of travel, that sort of thing. Okay, that's that. Number 7, a group of 12 men and 4 women. A group has 12 men and 4 women. If 3 are selected at random from the group, what is the probability that they all are men? Okay. And then this is just testing whether you recognize that these probabilities are related and accounting for removal. So it would just be the probability of selecting a man on the first selection times the probability of selecting a man on the second selection times the probability of selecting a man on the third selection. And then the second and the third are all given that you selected a man before that, and that's why those probabilities change. Right? So we take the man out of the group of 16. Now we have a group of 15 with only 11 men. And likewise for the next selection. Okay, at a college, 70% of students are women, and 50% of the students receive a grade of C. 25% of the students are neither female nor C students. Okay, so this is very similar to number 4. If a student has received a grade of C, what is the probability that the student is female? Okay, so this is what we have to do. What we have to do is we have to pick out what we know and then pick out what is being asked of us. Okay, so we pick out what we know. 70% of the students are women, so probability of W is equal to 0.70. 50% of the students receive a grade of C. Okay, so the probability of C is 0.50. 25% of students are neither female nor C students. Okay, so the probability that not female, so not W, and not C students is equal to 25%. So this is a value that's inside of our table. When we have this intersection probability, it's in our table. So this problem is going to be rather easy to kind of extrapolate all the information just like the last one. They become more difficult. Well, it's going to be not as easy, but fairly easy, okay? It'll be easy to complete the table in the same way. All right, so for the table, we go ahead and we put a 1 in the corner for our total probability, just like we always would, and then we put the rest of our information there. So all the non-highlighted things are the things that were given to us in the problem. Okay, and then we use, our probability rules and just good old logic to figure out the rest of the table. Okay, and so once we figured out the rest of the table, we have to answer the question. If a student has a grade of C, what is the probability that the student is female? So the probability, what we're asking to find, is of somebody being female, but it's given that the student has received a C. So this is what our thing is going to look like. Probability that it's a woman given that it's a C student. Okay? So we have a formula for that, right? That's just going to be our conditional formula. So we break this down, probability of W given C. We break it down into the formula because these are values that we have in the table, right? That's the only reason we do that. We solve this whole table out such that we can answer any question that is asked of us. All right. So probability of W given C is equal to the probability of W and C over the probability of C. We have both those values in the table. We pluck both those values out of the table, and we get 90%. So given that a student has received a grade of C, it is 90% likely that she is female, which makes sense. If we look at this table and we only look at the C column, we have 0.45 of the C's are in the W column and 0.05 of the C's are in the not W column. Okay, so that's 90% of that 50% probability, which that's the logical way to look at it. Okay, let's move on to number 9. Sorry that this is in weird order. Which of the following is not a discrete random variable? The number of times a light changes red in a 10-minute cycle, the number of minutes required to run 1 mile, the number of defects in a sample selected from a population of products, the number of criminals found in a 5-mile radius of a neighborhood. So we know that it's B, because B is the only continuous thing, right? So not discrete would be continuous. But let's just talk about why A, C, and D are in fact discrete. And this might be obvious to you, so if I'm over-explaining, I'm sorry. But the number of times a light changes red in a 10-minute cycle. Could you ever have a decimal number there? No. A light could never change 1.5 times, right? The expected value of it could, but like the actual occurrences couldn't, right? So because it can't be a decimal, we know that it's a whole number, thus it's discrete. C, the number of defects in a sample selected from a population of 100 products. Could you ever have a half of a defect? No. It's either a defect or it's not. Okay, so that's a whole number, so we know that it's discrete. The number of criminals found in a 5-mile radius for a neighborhood. Again, can't have a half of a criminal, right? So we know that it's discrete. The number of minutes required to run 1 mile. That is continuous, right? We could have any number. It could be 4 minutes and 23 seconds. It could be 4 minutes and 23 seconds, 0.23. It could be 4 minutes and 23 seconds, 0.2354. So it's on this whole continuous spectrum, all right? Don't think of it in terms of like, oh, well, you said minutes, like it has to be in minutes or anything like that. No, it's time. So time can be measured infinitesimally, really, really, really small. You like how I use the word infinitesimally? Makes me sound smart. There you go. All right, anyways. All right, number 10. While conducting experiments, a marine biologist selects water depths from a uniformly distributed collection that vary between 2 and 7 meters. What is the probability that a randomly selected depth is between 2.25 and 5 meters? All right, so the crux of this problem, or any type of problem here where we're like asked to use a probability distribution function, is to realize that like it's more than likely going to tell you in the problem how to solve it, right? So this says uniformly distributed, okay? So what I'll tell you guys right now is that how many distributions do we have? We have like a generic discrete distribution. That's where we list the x values and the p of x values, Okay, we have a, I guess the most generic form of the continuous is the continuous uniform, right? It's just a flat line. So we have the discrete generic, we have the continuous uniform, we have a normal distribution, we have a Poisson, and we have a binomial. And those are the only ones that we've learned. So we just have 5 different distributions, all right? Okay, the uniform is always going to be told to you, right? It's always going to say, oh, it's uniformly distributed. All right, that's that. Okay, so you'll know, well, I have these uniform, formulas that I can use on this. And you'll have those formulas for the test. I'm giving you as a term sheet that you get to use in the test, okay? The normal, it's always going to tell you that it's normal. The Poisson, it's always going to tell you that it's Poisson. The only 2 that it doesn't tell you, okay, are binomial and the generic discrete one. The generic discrete one, you're just going to know because it's going to be in a table form, right? It's just going to have an x values listed and then p of x values listed. So you'll know what is discrete. Binomial, the way that you figure out if it's binomial is, does it seem to have an n number of trials? Okay. Does it seem to have a p value that is consistent and independent, right? Meaning the probability doesn't change. So it's a probability of success. And then, are there just 2 options, right? Is it binomial? Is it binary? Like, is it success and failure? Can you view it like that? So that's how you determine those. But 3 of the 5 that we have, it tells you, and the other 2, it's obvious. One of them is just the only distribution that looks like that, where we list x values and list p of x values, and the other one is just the other one, right? I just described that. So that's that. So for number 10, this is uniformly distributed. So the formula that we use is, f of x is equal to 1 minus, I think we went with 1 minus f of x is equal to 1 over b minus a for our f of x. That's going to end up being the height of our graph. And that's defined from a to b. Okay? These are the endpoints of the distribution. So in this specific example, it's uniformly distributed between 2 and 7. So 2 is our a, 7 is our b. So the beginning of our distribution, the end of our distribution. Okay, here's the graph here, from 2 to 7, and its height is 1/5, so 1 over b minus a. And so then what is the probability that a randomly selected depth is between 2.25 and 5? Well, we just say the top end of that range minus the bottom end of that range, so d minus c, essentially, over the top of our whole range minus the bottom of our whole range. And that's that. And that calculation is pretty self-explanatory. Okay. All right, now on to number 11. During the past 6 months, 73.2% of households purchased sugar. Assume that these expenditures are approximately normally distributed with a mean of $8.22 and standard deviation of $1.10. Find the probability that a household spent less than $5. Okay, so this is our standard normal distribution. One, it tells us that it's normally distributed, so we automatically know the set of formulas. And when I say the set of formulas, we have one formula that we use for this. It's just z is equal to x minus mu over sigma. Okay, so let's look at our problem. We pick out our mu, mean of 8.22, sigma, standard deviation of 1.11, and then it's asking us find the probability that the household spent less than $5. So we automatically, would write out probability of x less than 5. Okay, then the next spot, what we would do is we would convert our x value into a z value. So we do that with our z formula. We say 5 minus 8.22, so 5 minus our mu over our sigma is equal to something, and then it's ultimately equal to negative 2.93. And then we go, because this is a less than probability, and because our table is set up cumulatively, meaning that it's always going to give us the less than probabilities on the table, We just go when we find z is equal to negative 2.93. Okay, and that's going to give us 0.0017, and that's that. Okay. All right, I think I'm just going to do a few more here because I think that'll just about cover all the concepts that we need. Suppose the distribution of personal water usage in New York City is normally distributed with a mean of 15 gallons and a variance of 25 gallons. Note that it says variance and not standard deviation. Because of a current problem with the distribution of water to its citizens, the mayor wants to give a city tax rebate to the 15% of the population who use the least amount of water. What should he use as the water limit for a person to qualify for a city tax rebate? Okay, so this one is different than the one before. One, we do know that it's normally distributed, but this is that other way of using our z formula. This is not when we are asked about an x in the problem. This is saying, hey, you need to find an x, right? We have information about the percentage of the distribution that we know, but we want you to find an x. We want you to find the actual x value that is related to the percentage of the distribution that we know. Okay, so again, we write the things that we know. So we know what the mean is. Mu is equal to 15. Okay, and it gives us the variance, and then we can just logically extrapolate like what the sigma is from that, what the standard deviation is from that. So we have a sigma squared is equal to 25, or variance is equal to 25. So our sigma, or our standard deviation, is equal to 5. Okay, so now here's the portion of the problem. So this is why I draw a graph here. Because of a current problem with the distribution of water to its citizens, the mayor wants to give a city tax rebate to the 15% of the population who use the least amount of water. So he wants to know what amount of water is the bottom 15%. Okay? So in order for you to figure this out, you need to figure out, well, what is the z value that equates to the bottom 15%? So I just draw a little graph here, and I say we need to know the z value that relates to 15% below that line. Okay? So what we do is we go to our z table, and we look for 0.1500, or something really, really close to it. Okay? Inside the table. And then once we find that inside the table, we then look out and say, okay, well, what is the z value that equates to this? So if you go to the table, so let's look at our table and find this. All right. Okay, so we're going to scroll to our normal distribution, which, like I said, you guys will have this on the test. So our z tables, as we call them, we know that it's going to be on the left-hand side of the table, so it's not going to be on this positive side of the table. It's going to be on the left-hand side of the table because it's a value that is less than 50%. Right, this table goes up to 50% because it's the left-hand side of the normal curve. So we're just basically looking for where about 15% of the data is. Okay, so I kind of just am going to start. You can kind of start in any corner and then just move in the direction until you see 15%. So I'll start in the bottom right corner and kind of move up. Okay, I'm at 16%, right around 0.9. Then I pass it. So now I'm at 0.1379. So now I'm going to move over. We're trying to find 15%. Okay, so here we got 15%, somewhere close to it, so we're kind of in between, right? 0.1515 and 0.1492. So you can honestly use either z value from this, right? So the z value, if we look to our left, negative 1.03 or negative 1.04, okay? All right, so negative 1.03 or negative 1.04. It looks like in this I decided to use the negative 1.04. It's fine. Either one is going to get you the right answer, or something close enough to the 9.85. But anyways, so we have a z-value now, and then we just plug that into our formula. So we have a z-value and we solve for x. And once we do the arithmetic and all that, solving for x, we get 9.85, or a number close to it. So this would be our best answer, A. Okay, and on to number 13. Blank is the science of using a sample to make generalizations about the important aspects of a population. Time series analysis, descriptive statistics, random sample, or statistical inference. And just based on your definitions, if you know your definitions, it's statistical inference, right? Descriptive statistics just describes, hence the name, just describes whatever data that you're looking at. Statistical inference means you're taking statistics of a sample and you're applying those generalizations to the population. Random sample is just a random sample. Time series analysis is one of those nonsensical answers that means something completely different. Okay? Compute the variance of the following sample data set. So this is just, do you know how to use the formula for variance? So the first thing we need to do is we need to compute the mean. And I actually made an error in this. Not good. I actually made an error in this, and it's only an error with a symbol. And that should say what is x bar, not what is mu. Because we're working with a sample, this should be x bar. X bar is the mu for a sample, or x bar is the mean for a sample. Mu is the mean for a population. So it calculates the same way for our mean. Yeah, so that's that. So we first need to calculate the mean. The mean happens to be 3. So this whole data set over the number of data points. Okay. And then we take each data point value, each x value, we minus the mu, square it, sum those up, and divide it by n minus 1. Right? So you can look on your formula sheet, or you can look at your variance formula and see the formula of how to do this. Okay. The next one I want to look at is 27, because we haven't covered a binomial one yet. So let's cover number 27. A recent study stated that in U.S. colleges and universities, approximately 25% of all professors are women. I don't know why there's so many men and women problems on here. That's kind of annoying. Anyways, if a student takes 6 classes this term, all with different professors, what is the probability that at least 2 of the professors are women? And then B, what is the at most 2 professors are women, and then all professors are men. Okay. Actually, I think men and women makes a lot of sense on here, because there's only 2 options, right? And then that kind of lends itself to using the binomial, because just 2 sides of the coin. All right. All right. Okay, so we know that this is binomial y, because we have a set n, right? N is going to be 6. If a student takes 6 classes, so this would be 6 trials, essentially. And we have a consistent p-value, or a consistent p, which is equal to 25%, or p is equal to 0.25. Okay? So then we would just go... I'm not even going to show you how to do the calculations. We're just going to look at how to use the tables, okay? So we know that n is equal to 6, and our p-value is equal to 25%. So we go to our table, we look for binomial tables. Binomial tables, we find n equals 6 table, and a p-value that is equal to 0.25. So the column kind of right in the center here. And then we are looking, we want to know at least 2 of the professors are women. All right, so at least 2 of the professors are women. So that is going to be probability of x is greater than or equal to 2. Okay, and we can say, well, we can either do that one of a couple ways. We can then just add up the probability that x is equal to 2 plus the probability that x is equal to 3 plus the probability that x is equal to 4, probability that x is equal to 5 plus the probability that x is equal to 6. We could add all those up and that would be fine. Or we could do it a simpler way and say, well, we know the total probability is 1. So why don't we just say 1 minus not what we're talking about. So that would be 1 minus the probability that x is less than 2. Which is the same as saying 1 minus the probability that x is 1 or less, right? Less than or equal to 1. And then that's easier to calculate. It's just the probability that it's just going to be equal to 1 minus the probability of x equal 1, which is 0.3560, minus probability that x is equal to 0 of 0.780. And that ultimately equals 0.4660. Then it says, for B, what is the probability that at most 2 of the professors are women? So at most, meaning probability of x is less than or equal to 2. So that's easy. We just add up the probability of x equals 0, probability of x equal 1, probability of x equal 2. So add up 0.1780, 0.3560, and 0.2966, and that gets us 0.8306, and then the probability that all the professors are men, which is just the same thing as saying that none of them are women, right? So it would just be the probability that x is equal to 0, which we know from just grabbing from the table, 0.1780. That's that. Cool, guys. Well, I'm going to cut this video short because it is running very long. Oh, and I'm getting a call, apparently. Anyways, I'm going to cut the video short. And, yeah, if you have any questions on any of the other problems, get those questions to me before Friday, before the exam window starts. So today or tomorrow, and I'll answer them. But you should have pretty much what you need to get going for the test. We've obviously covered all of this stuff in detail and a bunch. But if you have any last minute things, please let me know. I'll be happy to answer them. And happy studying. All right, bye.